And within this trial, 553 patients with a severe sprain of the ankle were randomized into one of 4 treatment groups. And the clinical status for these patients was measured at 4 points in time via the foot and ankle outcome score, which is a questionnaire of 5 subscales and 42 items. For the purpose of this talk, we will be focusing on only one of these subscales, the so-called symptom subscale. And for this subscale, a score ranging between 0 and 100 was calculated, where 0 corresponds to extreme symptoms, whereas 100 corresponds to full recovery. Now, the aim of the study is to estimate the clinical effectiveness of the treatments plaster of Paris, Aircast brace, and Bledsoe boot compared to the standard treatment tubic grip. Now, in order to have a first idea about the study, I have plotted the individual evolution for a couple of patients. And the first observation we can make is that the score appears to be a monotone increasing function of time, which is quite clear. But furthermore, it strikes out that the score increases much faster at the beginning of the study than towards the end of the study, which motivates that we are aiming to model the rate of improvement rather than the overall mean. Now I want to draw your attention to the dashed line, which corresponds to patient with missing observations, where the red dashed line corresponds to a patient who drops out after the 3rd point in time, whereas the black dashed line corresponds to a patient who shows a non-monotone missingness pattern, as only the 2nd observation is missing. However, in this talk, I will be really only focusing on monotone missingness. Now, a bit more details about the missing data that we observe. We observe our symptom subscale completely for all points in time, just for 67% of the data. Now, missing data are a very commonly observed feature of longitudinal studies, and the reasons for missingness usually occur outside the control of the investigators. And depending on the reasons for missingness, we distinguish between 3 missingness processes. A missingness process is termed missing completely at random when missingness doesn't depend on any observed or unobserved measurements. A missingness process which uses less restrictive assumptions is the missing at random process, where missingness is allowed to depend on observed quantities such as explanatory variables or the observed outcome of interest. Now, a subclass of missing at random processes are the so-called ignorable processes, where in addition to missing at random, we have that the parameter vectors associated with the measurement process and the missingness process are disjoint. And it has been shown that in this case, we can base likelihood inference just on the observed data. And now finally, if the missingness probabilities do depend on unobserved quantities, we term the missingness process missing not at random. Now in our CAST trial, we observed that patients with a low baseline score or a relatively high score at the 4-week or 12-week time point do not return the questionnaire for the following point in time, thus suggesting that our missingness does depend somehow on the previous outcome of interest, which leads us to missing at random. However, a second study conducted by the Warwick Medical School in order to investigate the reasons for missingness revealed that patients who considered themselves to have made fully recovery didn't return the questionnaire. Therefore, missingness also seems to depend on the current unobserved score. Now, in the case of non-ignorable missingness processes and informative missingness, as it's missing not at random, we need to explicitly model the missingness process. And we intend to do that by taking into account some additional information that we have. And this additional information consists of the number of reminders needed to retrieve a questionnaire. And the investigator have set up the system of reminder letters where we distinguish between these 6 categories, where Z equals to 1 corresponds to no chasing was necessary, we got the questionnaire back straight away, where Z equals to 6 corresponds to non-responders. Now we have different categories, so it's like we call them again, we send other copies of the questionnaires. And this reminder process is a process which evolves in time. That is, if the first attempt is not successful, I do the second attempt. If the second attempt is not successful, and so on. Now, we would like to adjust for missingness using this reminder process. And this is, the idea is quite straightforward, as when the measurement is observed, this is equivalent to Z being one of these in one of these categories. And if the measurement is missing, it is just equivalent to z equals 6. So just to briefly summarize again what we will be doing, we want to compare the treatments by modeling the rate of improvement, taking into account the longitudinal and bounded nature of the score, and at the same time the reminder process in order to adjust for informative or non-ignorable missingness. Now we will say some more words about informative or non-ignorable missingness. As I said, here we need to model the measurement process and the missingness process jointly. So in more detail, let yi be the observation vector for subject I, which we partition into the observed and the missing part, that I be the vector of the reminder categories for subject I, xi summarizes the explanatory variables. We then assume that the outcome vector follows a parametric model with parameter of interest theta, and the conditional reminder process follows the parametric model with the parameter of interest psi. So as we need to model both jointly, but we can base inference only on observed information, we need to integrate out the missing data of the joint likelihood. So this is just the likelihood contribution for the subject I. And now, dependent on the model that I choose for this joint density, we distinguish between, in the literature usually, between pattern mixture models, shared parameter models, and selection models. And I will be focusing here on selection models. That is, I factorize this joint density into the marginal measurement process and into the conditional reminder process. That is, we now need to formulate a model for the marginal outcome process and the conditional reminder process. So we'll start with presenting the model that we use for the marginal outcome process. Here I plotted the average evolution for the different treatment groups, and we now aim to formulate a model that meets the characteristics of a longitudinal study, but at the same time accounts for the bounded nature of the score. And commonly used models for modeling continuous longitudinal data are usually multivariate linear models, random effects models, or marginal models. Now, all these models would model basically a linear regression, taking into account the correlation between the measurements of one subject. However, they wouldn't really enable us to estimate this asymptote which we observe. And secondly, they wouldn't really model the rate of improvement in which we are interested. So we will formulate a nonlinear mixed model which bases on the assumption that the rate of improvement at a certain point in time depends on the current score where I am and the still achievable score. Okay, to see that in a bit more detail, let yij be the observation of subject I at time point j. We then assume that given a random effect, this is normal distributed with mean eta ij and variance sigma square. Furthermore, we assume that the random effects are normal distributed with mean 0 and variance d square, and we formulate this model for the mean components, where g is the model function which we need to specify, xij are the explanatory variables we want to take into account, and theta I is the parameter vector of interest, which we assume to vary across different subjects in order to account for the between subject variability. Now what I need to do is to specify this function g. And as I said before, we will specify the function g based on the assumption that the rate of improvement is proportional, and this proportion factor will depend on the treatment, to the current score and its still achievable score, where maximum is this asymptote that we observe. Now, solving this differential equation, taking into account age, treatment, and time as explanatory variables, leads to the following model function, where we add a random effect in a linear fashion. So this model might look quite complicated, but the interpretation is very simple, because beta naught simply denotes the intercept of this curve, and beta 1 plus alpha 1 times h models the asymptote, so the maximum of our curve, and beta 2 plus alpha 2 times h models how quick do I move towards the asymptote. I'm not including an h effect on the intercept because primary analysis showed that that is not significant. So this is a model for the outcome model, and now I have to specify a model for the conditional reminder process. For this purpose, let's set J be one of these categories. I'm omitting the subscript I for the subject here because otherwise it would look too complicated. And let pj1 be the probability to respond at time point j and at the very first attempt. Okay? Furthermore, let pjk denote the probability to respond at the kth attempt, given I haven't replied earlier. Then the unconditional probabilities to reply at attempt k and time point j are given by mu j1 to mu j5. And thus, the probability to not reply at all is then given by 1 minus the sum of these probabilities. So now I want to formulate a parametric model for this reminder process. And in order to do that, I first redefine the Zj in terms of a 6-dimensional random vector Vj, which simply indicates which attempt was successful. And we then assume the following model. Vj, given our outcome of interest, is assumed to be multinomial distributed with parameters mu j1 to mu j6. Now, the question is, should I formulate a generalized linear model for the mu j's or for the pk's? But now we know that the reminder process is the process which evolves over time. So it seems more plausible to formulate a model for the pjk's because they actually say what is the probability to reply at this attempt given I haven't replied earlier. So that is what we did, and we tried to fit these different missingness processes in the context of a sensitivity analysis, where all these missingness processes do depend on time and the treatment Bledsoe, which was shown to be significant in previous analysis. And in the case of missing at random, we further assume a dependence on the previous observed outcome, and in the case of missing not at random, on the previous observed outcome, but also the current, maybe unobserved outcome. So some of you might say now, this is not really missing completely at random, and I do agree, but the thing is, what I'm saying is that given covariates, the missingness process is missing completely at random, so that's why we use this. And further, I assume that the intercept depends on in which attempt category I am. And primary analysis under the assumption of ignorability showed that the intercept for the first attempt, the third, and the fifth attempt category can be assumed to be 0. So now I want to show you the results we got. So here I'm comparing those 3 missingness processes and the results for the ignorable missingness process, that is, where we don't model the missingness process at all. And let's first focus just on these parameter estimates for the outcome process. Now, beta naught, just to remind you, is the intercept, and as you can see, there's really no difference. It is very robustly estimated across all the different models we tried. Now, beta 1 plus alpha 1 times h models the asymptote of our function. And you see that for those 3, it is again, the results are very similar, only for the ignorable missingness process, they differ slightly. However, if you plug in the average age of 29, you will see that the asymptote which you reach is actually the same. So the age effect just varies a bit here. Now alpha 2 is the effect of age on the slope of how fast we get to the asymptote. And this again just differs slightly for the ignorable process, and the sigma square for the within individual variation is pretty stable, and also for the variation between the individuals. We again just underestimated slightly for the ignorable process. Now let's turn to the parameters of the missingness process. Here we see that all, like for psi 02 and psi 04, that these are positively, like they have a positive sign. That means that the probability to reply for these attempt categories, which correspond to calling the non-responders again, seem to be higher. So calling the patients improves the probability to return a questionnaire. However, the amount kind of differs for the different missingness processes. Now we also see that time has a negative effect on the probability to reply. That is, as time passes, the probability to reply decreases, which is something we would expect in a longitudinal trial. And then the Bledsoe treatment as well seems to have a positive effect on the response probabilities. They vary a bit, and we will discuss that later on. But now let's turn to psi 2 and psi 3, our main parameters of interest. So psi2 is the dependence on the previous outcome. And in the case of missing at random, we see that this estimate is significant, and therefore suggesting that the higher the score is, the less is your probability to reply at a certain attempt. And therefore it agrees with the second study conducted, which revealed that patients who considered themselves to have made fully recovery didn't return the question. Okay, sorry. And then in the case of missing not at random, we see that there's the effect of the previous and the current outcome is not estimated to be significant. However, this might be highly due to the fact that yj and yj minus 1 are highly correlated. So we actually fitted this model with only dependence on the current score, and we obtained a significant effect there. Now I want to turn to the parameter of interest, because at the end the parameter of interest is the treatment difference. And I multiplied those parameters by 100 because there was really no difference at all. So I just did that in order to show there might be a slight difference, but those treatment differences are very robustly estimated for all approaches. And I'm just showing again the effect of Bledsoe, because this effect does differ substantially with the different approaches we assumed. However, this doesn't have any effect on the treatment difference when we assume the Bledsoe treatment. That's something we are not understanding yet, and we will have to investigate that in more detail. So now the conclusions. We have presented a selection model framework that uses a number of contact attempts to adjust for informative or non-ignorable missingness. This model combines a nonlinear mixed model for the underlying response model with the logistic regression model for the reminder process. We have seen that the treatment differences are estimated robustly across a range of plausible reminder processes, and the results suggest that phone calls are more effective in retrieving questionnaires than just sending further questionnaires. Furthermore, we have seen that patients who reply early tend to have more symptoms than those who reply at a later occasion or not at all. Now a couple of words for future work. As you have seen, we have only used all these results based on the assumption of monotone missingness. However, usually longitudinal studies have non-monotone missingness patterns, and therefore we need to take that into account. Then, if you remind, I have added the random effect in a linear fashion, and if I would write this model in a multivariate form, I would see that we are actually assuming a compound symmetry covariance structure, which is not realistic given that the lags between the different observations have different length. And furthermore, if you would draw the box plots for the different points in time, you would see that the residuals are highly skewed and therefore questioning the normality assumption. But Jane will talk about that a bit more. So thank you for your attention. Thanks to Sally Lamb at the Warwick Medical School for the data, and this is the literature. Thank you.
Okay, so I'll talk a bit about background, so what quality of life is, a bit about missing data, but as I said, I can probably miss out some of that. And I'll talk about the example data sets I've got, and then what I've done with the reminder data, and then finally conclude. So I'm sure quite a lot of you are aware, but it might be the odd one that's not. What is quality of life? It measures health status. So in this context, we're talking about things like physical functioning, social well-being, cognitive function, all these kind of things that go into kind of how you get on in everyday life. This is usually measured with questionnaires. These come in the form of generic questionnaires or disease-specific questionnaires. So with generic questionnaires, talking about things like EQ5D, SF12, SF36. So specifically today, the data I'm going to use is for the EQ5D. So that has 5 questions, one on mobility, self-care, usual activities, pain, discomfort and anxiety, and then the answers to those questions are amalgamated into a score. So you've also got disease-specific measures. So they're aimed to measure the quality of life specific to a particular disease, suggested by the name. So for example, the Oxford Knee Score, it's talking to do with knee functioning questions. So, you know, can you do your usual activities? I'll get back on the screen. Okay. And then another questionnaire there is the QRQC30. That's specifically for patients with cancer, and that comes with a lot of other modules as well, specific to the cancer in question. Okay, so what do I mean by missing data in the context of my talk? Well, I'm talking about non-response to a postal questionnaire. So I'm talking about missing forms rather than missing items. It's a problem because of the loss of power due to reduced sample sizes, and also you may introduce bias to results because the people who aren't responding are perhaps different to the ones that have responded. And so it is a problem with quality of life because quite often the reason why it's missing is the quality of life itself. So if you were to ignore that point, then you're going to end up with bias in your results. So this is probably the slide I can skip over because Mouna's already explained it, but we've got the 3 missing data mechanisms. So with quality of life, I'm talking missing completely random when it's dependent on perhaps covariates in your data set, so age, gender, that kind of thing. Missing at random, it's dependent on the observed quality of life scores you might have, but it's independent of the missing ones. And then the last one, missing not at random, when it's dependent on the missing information you've got about that outcome. So dealing with missing data, you've got a number of options. You could ignore it completely and just get on with your complete case analysis, which we all know is probably not the way forward, but is still commonly done. You could use imputation, so substituting in an alternative value. So you've got simple imputation, just a single value, or multiple imputation where you impute several values, analyse your data sets and combine it all together at the end. And then the last one, the model-based procedures, which I'm not really going to talk about, for example, the pattern mixture model, which is more the kind of thing Mouna's already talked about today. So the 2 example trials I'm going to use in today's talk are carried out by the Health Services Research Unit in Aberdeen, which is not the unit I'm part of, but it is another one at the same university. It's the record trials, the first one, so it's got just over 5,000 patients in it, and it's to do with vitamin supplementation in the elderly to prevent refracture. The treatment comparison I'm going to talk about is calcium versus no calcium. That wasn't the only one in that trial, but that's the one I'm going to use the results for. And as I said earlier, the quality of life measure used here is EQ5D. The analysis method they used when they reported the trial results was an ANCOVA for the 2-year time point, adjusting for the baseline quality of life and some other patient variables. Now, the quality of life information was collected at repeated time points in these trials, but they only ever analysed the final endpoint, adjusting for the baseline, and ignored all the interim responses. And I'll come back to that later on. So in the second trial by the same unit was the reflux trial, much smaller trial. This compared surgery with medical management for gastroesophageal reflux disease. And the final endpoint of interest there was the 12-month time point, and it adjusted for the baseline quality of life and a couple of the patient variables. So the quality of life outcome there was the reflux quality of life score, which was specific to that trial. So the difference between these 2 trials really is that the reflux trial, the quality of life outcome was actually the primary outcome, whereas in record it was one of the secondary outcomes. Okay, so again, these trials used a reminder system, so slightly different to Mouna's talk. There was no telephone reminders in this, it was a straightforward postal reminder. So if they responded straight away, I'm going to call them an immediate responder. If they responded following one of the 2 reminders, which were sent at 2-week intervals, I'm going to call those reminder responders. And then finally, you've got the non-responders, those who didn't respond at all or perhaps weren't actually sent the questionnaire because they'd withdrawn for some reason. Okay, so the response rates for these 2 trials, with record, the initial response rate was 51%, but you generate an extra 14% by using the reminders. So the overall response rate was a 65%. In reflux, the initial response rate was very low, it was only 38%, but the reminder responders generated a huge amount of extra information, so you got an additional 51, giving you 89 in total, which for clinical trial kind of postal follow-up questionnaires, people should know that that's rather good. But if you hadn't used the reminders, it would have been pretty rubbish. So it highlights the importance of those there straight away. Okay, so what did I actually do with all this data? Because I wasn't involved in these trials, I just get all the data from them to do what I want to do. I've used this extra reminder responses to kind of look at ways of dealing with the missing data. So I looked at the missing data mechanism, tried to find out what it was, and I'll just talk briefly about that. And then I looked at using imputation, whether it is useful, which particular methods are useful, is it the same across all trials, that kind of thing. So with the missing data mechanism, this is the only slide I'm going to talk about, so if you're really interested, read my paper, which recently came out on all this stuff. So I used 2 hypothesis tests for looking at missing data mechanism and 2 logistic regression procedures, and kind of looked to see whether they came out with the same answer in terms of what the missing data mechanism was. So I first looked at the non-response mechanisms. That's what you typically look at. And so for record, that was found to be missing at random. I also looked at the mechanism behind reminder response. So was that similar to the, were people responding completely at random by reminders, or was something going on? Why were they responding by reminder? And as Mouna's already said, you perhaps think that the people who respond by reminder are perhaps more similar to those that don't respond at all, and they just needed a little bit of prompting, or maybe, that extra week they're feeling a little bit better and they wanted to respond. So in reflux, it was found to be missing completely at random in both cases, and this is important in a bit later on as well. So moving on to the imputation methods. For this part of the work, I took the subset of all the data that all the people that responded at that main endpoint. So remember, in record that was the 2 year, and in reflux that was 1 year. Took that subset of responders, removed the data that had been collected from the reminder questionnaires, carried out various methods of imputation, and then repeated the ANCOVR that was originally used on the data. And then you could compare the result from that ANCOVR on these imputed data sets to the result that was published by the trial researchers. And then the idea of this was to try and identify which might be the best method of imputation, if any, to use on the actual missing data to help boost your sample size that you've used in analysis. So, I'm not going to bore you with lots of tables on that. I'm just going to pick out what I actually found out, partly for interest of time. So in both cases, actually, it was... sorry, wrong button. Okay. Last value carried forward seemed to be the best simple imputation method, which I'm sure, as everyone knows, isn't generally recommended. But for whatever reason, in these trials, it was, and I think that's perhaps by nature of the trials, they generally had stable quality of life across the time points, which is perhaps why this was useful here. However, the multiple imputation method using a predictive mean match model was superior to the simple imputation. But of all the simple imputation methods I considered, last value carried forward did seem to come out as the best. So the key things really here were that in record, the different imputation methods did have an impact on what you would have concluded about the treatment difference. So that highlights that it's important to think about what method you're going to use, because it would have altered the conclusion if you'd gone down the road of imputation. And that ties in with the missing data mechanism, because the simple imputation methods there weren't so good, and that was probably because the missing at random mechanism was there, and simple imputation generally assumes missing completely at random, whereas multiple imputation was much more appropriate. In reflux, the trial estimate of treatment difference was highly significant, and the methods of imputation didn't seem to affect the conclusion, but the magnitude of that estimate was different. Okay, so moving on to that was an earlier stage of my work, and then this is the kind of latter part, where having looked at this imputation method, I was also interested in whether different analysis strategies that you could have used would affect your estimate of treatment difference. So there's 8 there. Essentially, we've got on each type of method I've carried out on the immediate responses, so I basically ignored anything I collected was collected by reminder, carried out the analysis method, so ANCOVR, repeated measures, some imputation and so on. And then I've also taken the data which actually, as was collected, all of the reminder responses as well, and carried out the same analysis strategies. So, it's a bit confusing, but hopefully it will make sense. So, apologise for the slightly large table, but I'll just highlight what I want to show you. So these were my strategies down on the left-hand side. You can see straight away that the different strategies are going to use different numbers of patients. So remember, this is at the final endpoint. If you'd not had any reminder data and you'd carried out the analysis strategy that the trial researchers did, you would have only used 36% of patients, which isn't a whole lot. So that probably wouldn't have been a good idea. This second one is the one that was actually published for the quality of life outcome. As you can see there, they've actually only used 54%, but it was a secondary outcome, so it's potentially not so crucial. But if you look down here, using all responses, and this it was a mixed effects model I used, you used 74%. And these type of approaches perhaps were more helpful for this study, because it was collected longitudinally, the quality of life, And by ignoring all the intervening time points, you've lost a lot of information, and they have been helpful because this then assumes the missing at random, which I showed earlier, was perhaps what was going on in this trial. And again, you can see that the magnitude of the treatment difference does differ across the different analysis strategies. So that's just it pictorially, if you're more into graphs. So you can just get an idea of, different confidence intervals, different estimates, and so on. And at the bottom, I've got the numbers. So that was record. So that was the big trial, the 5,000 patient trial. So for reflux, got the same kind of table. I've ignored the p-values this time because they were all highly significant. Again, you can see that the different numbers of patients were involved in the analysis. So it's the same kind of strategies. Remember, this was a predictive mean match model for the multiple imputation. In this instance, the mechanism was found to be missing completely at random. And given that your ANCOVR up here used 77% and it was missing completely at random, this perhaps was the best strategy to use, because you probably wouldn't want to go, if you've got that much missing data still, you might not want to go down the road of imputation, and given that it seems to be missing completely at random, this was thought to be probably the best strategy in that instance. Whereas in the previous one, having done all the work, not got time to talk about everything I've done, but this one probably would have been better in that trial. Okay, so back to reflux. And then you've got the graph there, so you can just see the difference. This one here, which is the lowest one, was number 5. So it's that one. So you can see that that was probably that would have been a really rubbish strategy. So basically this highlights the importance of the reminders, because you're getting this extra information, and the previous work has helped you decide which might have been the better imputation strategy if that's what you wanted to do. Okay, so a lot of, when I talk about these things and colleagues and other people and so on, they're all saying, well, what shall I do if I've got a trial with missing data? Well, I think perhaps a fairly obvious statement, but quite often ignored, I think, by people who are planning studies, is you should try and minimise your missing data. Inevitably, you are going to have some, but if you try and plan your study to minimise that as much as possible, then that's going to be helpful. Using reminders for this, I think, is quite key. And again, Mouna mentioned the use of telephone reminders. They weren't used in this trial, but I think that is something that this unit is getting into a little bit, and I hope to do a bit more research with that in the future. So you will have missing data, it's inevitable. Even if you can plan it perfectly, you're still going to have some. So what are you going to do if you do? Well, firstly, you need to identify the missing data mechanism, because you can't decide on the best approach to deal with it if you don't know what the mechanism was, because even the different approaches have different assumptions. So if you did have missing completely at random and there wasn't too much missing data, then complete case analysis or perhaps a sensitivity using some kind of simple imputation might be appropriate. If you've got missing at random data and you do have this kind of longitudinal nature, then you might want to use this mixed effects models, because you can make use of the information collected at earlier time points. So patients who didn't provide the final endpoint can still be included in the analysis rather than just ignored. And then finally, missing not at random, you've got the model-based strategies which Mouna talked about, and pattern mixture models and things like that. So the reminder data that's been collected and all this work I presented has helped you kind of decide which might be the best method. Okay, thanks. Because you can use that extra information to help figure out what might be your most appropriate strategy, because you've collected this extra information, so you might as well use it in some way. So, it's the final slide. So in conclusion, I think the reminder system is an extremely useful way of recovering this originally missing data. It can be a cost-effective use of resources to help maintain your sample size, and you can use that extra data to help reduce the threat of bias. And then you can also, as I've discussed today, you can use it to inform the selection of potential imputation methods or decide which strategies are most appropriate. And then finally, just to acknowledge all the colleagues, these people provided the data, and the project and that unit was funded by the Scottish Executive, and these are my supervisors and other people. So there we go. Any questions?
Right, well, I'd like to thank you all for staying the course and being here. I'm not currently using a mic, I don't think, but Simon's not making any particular... Yeah, somebody's giving me the thumbs up. Right, so you will be able to comment on two things I'm doing that I shouldn't be doing, because you've heard from Mouna. I'm not doing a detailed analysis of the missingness to start with, nor, in fact, of the rate of change, because what I was actually interested in was the fact that a lot of these health scores are designed actually not for health, but for problems, as Shona said, and therefore they tend to, when you're healthy, if you've got a longitudinal trial, everybody's going to land up healthy, and our dear old normal distribution might not be the best thing to be looking at. So we're going to have really skewed distributions. Now, one of the reasons we like using the normal distribution is it has all sorts of nice properties about adding things together, which are helpful in random effects and all our regression models. So in this trial, you've had an introduction to it already, and so all I would say in this is that I'm using a very slightly different part of the score from what Mouna was using. You'll see similar results, but not identical. Loss to follow-up, 25% at 9 months, if you count getting the core outcome as good enough. And as you've seen, that's a bit variable. The box plots over time, well, this is to... I personally much prefer this. This is the box plots you weren't shown by Mouna, but you can see from these shapes, for example, a box plot with no whisker, that this must be very skew and a lot of clustering up at 100. So what sort of models do we usually use? We use models of normal distributions. And if they're not normal, we quite often think of transformations. So if we just looked at the raw scores, we'd get that massive skewness. Well, one thing you might automatically think of is, well, if it's on a range 0 to 100, well, that's our old friend, the logit. We can just retransform the score. We'll get the full range. We're back to the nice familiar territory. Well, the QQ plots show a very poor fit. If you think, well, let me find the best possible transformation and use the box Cox, well, the best you could ever get is an almost uniform distribution at the last time, but the distributions change over time. And one thing they're not going to do is deal with the fact that you've got something like a mixture because of this bunching up at 100 by the end. So this wasn't completely unconnected with the fact that I felt like going and working in Perugia in Italy for 3.5 weeks with my colleague Elena Stangelini, whose name was on the front, and she's done quite a lot of work on the skew normal. What is a skew normal distribution? Well, a bit of it should look familiar because that's the standard normal density and that's the distribution function. So without this bit, we've got a normal. What is this doing? Well, it's basically shifting the probability density a bit to the right or the left, but in a way that's parameterized by two familiar type parameters. We've got a mean kind of parameter being subtracted. We've got a scale parameter. That's great. In fact, if I put alpha equal to 0, the 2 would multiply by half and we'd be back to our old friend. So basically, we've got familiar parameters plus a parameter which is allowing us to go skew. And for those of you who've done anything about selection, it's related to the idea that you're going to select one variable according to the value of another. Those of you who are in the medical side, publication bias, selection models, the probability of getting published depending on your values. Again, the same general kind of ideas. If you want some historical notes, I'm not going to go into a lot of detail. It's been in the literature for quite some time, 1966, about 40 years. But it started being generalized to multivariate and applied rather more by Adelchi Azzolini and colleagues from 96 onwards. And probably the Azzolini in 1999 is a particularly useful paper. And then there is an extended skew normal developed by Capitiano and Stangalini, my co-author, intended for use with missing data. So what happens if instead of looking at the normal model, we take a model that Mouna mentioned but didn't use? We're going to think of our form measurement as coming from a multivariate distribution with the typical regression kind of approach that we so often take. But the difference is going to come in with this error term being skew, because I haven't got it yet. If you look at the way the mean and the skewness develop, they increase with time very nicely. Well, let's have a look at a picture of that rather than anything else. And the red lines are giving you the fitted densities. Down towards the beginning, the original time point and the second measurement, you've got something that's not too far off elliptical. It'd probably be fine with a normal. But as we move up to the later time points, you can begin to see that having something that, instead of trying to do that, allows you to come skipping in like this, it's going to be rather a lot better. If we then looked at univariate regressions, we were just going to focus for this point on the last time conditional on the previous observations. The first three observations aren't most interesting for this distribution because they're not so different from normal. So we're going to look at the fourth occasion. So this is a skew normal model of the third measurement based on the rest. So it's your familiar regression model except for the form of the errors, and this is looking at a plot of the residuals. You can see the residuals are skew, and you can see the fitted line picks up the skew, but what it can't do is cope with this little lot of extra zeros. What are those extra zeros going to be? Well, they're going to be all those people sitting up at 100, giving you trouble. But if we look at probability plots of the residuals, pretty good. The one on the left is the normal, and it's dipping down from the straight line. The skew normal is doing rather better, still a bit of a problem at 0. Well, we thought the skew normal would solve our problem. It's not quite managing. So the other thought is, well, actually, if you think about people, just because they've got no problems with their ankles, we might not agree that they've got the same level of health. It might well be you can still go up into fitness levels. In health scores, some people are beginning to look at positive health rather than just not ill. But that means it's quite natural to think, well, maybe we should think about this bunching at 100 as censoring at 100. And if you do that, put an indicator function in, do a little bit of algebra, and you get a likelihood. Okay, that's the density, which for survival you would get the density for the observed values, and for the censored values, you've got a doubling up essentially of your distribution. We've also moved on to a different way of parameterizing just because its rho at that stage becomes a nicer way to put things in than the alpha. And you go away to your friendly favorite package and you do the numerical optimization. And you say, how much difference does that make? Well, it makes a lot of difference. Because these two are essentially the same model, we can just do a straight comparison of the likelihoods. And we've dropped by 120. Censoring is a far better idea. What other difference does it make? Well, it picks up a difference in treatments that we couldn't pick up before. So these are my codes for what Mouna had as a contrast between treatment and basic effect. One of the reasons, incidentally, these aren't showing up as significant in hers were is I haven't modeled that change process. This is just simple means. For some reason, one of those screens has decided to go blank. But then we thought, well, we rather like the skew normal, but was it necessary? Or is it all just censoring? And what this slide shows is that, although although the centered skew normal, it looks as though we've got a significant parameter. Actually, if you compare the likelihoods, we could have just gone back to our old familiar friend, the censored normal, and got very similar results. What happens if we actually looked at the different ways of estimating the actual mean value? Well, this is where we do see a difference, because if you're using a normal, which I haven't shown, or the censored normal, you really are not quite able to go high enough because of the skewness in the distribution. Whereas by using the skew normal, we are actually able to shift the mean of the distribution much nearer to the 100. So that's true, despite the fact that the likelihoods aren't making a big difference. So it's quite interesting that the fitted means differ quite a lot. Okay, somebody will ask me, are you sure you've got it right? That's usually the first thing to do when you get an interesting result, is try to find out where you've got the errors. But given that we have this censoring, one interesting question would be, how much data do you need to be fairly confident that you're detecting the difference between censoring and an actual skew underlying distribution? How much of a skew distribution could you censor to make it symmetrical, or vice versa? I've only presented the complete data. In fact, in the written paper, which will be submitted later today or on Monday, we've also looked at how you can assess whether there's much effect of dropout, and there isn't that much on the treatment effects. There is an effect on age. So I'd like to finish again by thanking my colleague for very kindly letting us play with their data after they've published the main results. Thank you.